placement. So all the analog should be placed together. So if you have a, let's say, analog and digital both, and most of the time we have on any chip both analog and digital. So what we do, we try to keep the digital and analog separate. So all the digital should be placed together and all the analog should be placed together, and we try to maintain some spacing. Don't keep them very close, otherwise again noise will get coupled from this, because it's switching and it may corrupt your analog signal. So that's why we always try to separate them out, and there are some guard rings and all those techniques you use to basically have a better isolation. So this is a resistor, laying out a resistor. So let's say I have here 3 resistors, okay, 4 resistors actually. So you have 4 resistors here. Now if I keep them interdigitized, so R1, R2, R3, R4, then R1, R2, R3. So you can see how the routing is so complex here. Huh? So what happens, you are trying to match the resistor, but this complex routing may introduce additional resistor and which may not match. Then you will get a mismatch from the routing, even though you have matched the resistors. So most of the time what we do actually, instead of breaking them in like, you can break them in unit, but instead of placing like this, you place all the 4 units here and connect them in series, then all the 4 units and all the 4 units like this. And if let's say you can split it in them 2 or 3 and you can repeat the same, or you can place them in common centroid. Okay. So routing is simplified here. Here routing becomes very complicated. Until unless your resistor value is very large, where routing will not affect. But if your routing resistance is comparable to even 1% of your, let's say, this resistor value, then it can easily introduce some mismatch. And 1% is not small when you are looking for your band gap reference and all those. So 1% mismatch is huge. Okay, so these are some guidelines for resistors and capacitors. So obviously the size rules for size applies here also. Don't try to keep them very small, otherwise mismatch will be more. Shielding, noise decoupling and shielding. So what happens if you have a critical signal, then so let's say you have a reference, you are routing a reference, and you have lot of digital signals going all the way. You don't want that digital to get coupled to your reference, otherwise it will create some noise. So what you do, you shield. So you route from top, bottom, left, right. So you basically create a shield on all the 4 sides. You can connect to with the mostly with the clean ground or any clean reference, so that in between you have only reference. And if let's say on the other side you have any clock going on, so your shield will block that. Okay, so let's say that is connected to ground, then the coupling capacitor will be between that signal and ground, not from that signal to reference. Supply and ground routing. So this is very important. So if you have analog and digital, so this is not the correct way. So this is your VDD pad. Never short them locally and then have a single metal connected to the pad. Always try to do this. Is called actually star connect. If you have a multiple bond wire, if you have option of multiple pads, then best thing is have a separate pads for them. But if you have only single pad, then always connect directly to the pad, not like this, that short here and then connect a single. The reason is, I mean, you have to look at the least resistive point, and this will be the, because this is the source. So when you connect the source directly and route them separately, then the chances of coupling between this and this are less. But here you have created additional resistor between this point to VDD, and now the signal can couple from digital to analog and corrupt your circuit. Okay. So this is called star connect. So this is the best option. If you have multiple pads, then separate out and then bond them to a single pin. But if you don't have that option, then at least try to make sure that they are routed all the way to the pad rather than shorting them locally. So, you follow this for both ground and VDD. Decoupling cap. So, always try to use a decoupling cap, and that should be placed as close as possible to the module. The reason is you want to decouple the noise here, and if I connect far away, then you will add resistance, and then it will looking like a ESR in the capacitor, and that won't be very effective capacitor. So, always try to place your decoupling cap closest to the module, not away from the module. This is just showing that how the noise gets coupled. So, one more thing you need to remember that we use lot of I just mentioned a guard ring actually. So, the guard ring is nothing but the contacts and diffusion put around your well and substrate. So, this is your digital, it is switching. So, you always have a capacitor between this source and bulk, that we already know. These are parasitic caps, and if this guy is switching, this capacitor will couple the noise and inject into the substrate, and this can propagate here and picked up by this. So, let us say this is a DC reference, and you again have a capacitor here. So, one way, okay, you can increase this resistor by separating them out completely. Okay. So, that is why I said you try to maintain some minimum space between analog and digital, so that you can, when this signal is propagating, by the time it reaches here, it is almost died out. Okay. So, but even if let us say there is a possibility of some signal propagating here, it can be picked up by through this capacitor and corrupt your DC signal. So, what we do here, so the best way to create a low resistive path which can pick this signal. So, what we do, we put this substrate contact here. Now, before it reaches here capacitor, this contact is connected to ground, and this will pick it up and remove this all the noise from here before it reaches to the signal, and that is why we use these diffusions or guard rings on both the device. So, depending upon whether NMOS or PMOS. So, if it is a PMOS, then it is created in N well. So, you use N diffusion N plus, and this is a P sub NMOS created in P sub. So, it has to be P plus. Okay. Because these substrates are lightly doped, and when you make a P plus, it is highly doped. So, it creates a low resistive path, and you connect with the contact and metal, you connect to the ground, and with the N well you connect to the VDD. So, in that case VDD will pick up the noise. Isolated P well. So, some process have option where you can isolate both. So, substrate is common. See here, substrate is common. So, if the substrate is common, which means digital and analog both are sitting in the same substrate. So, if I want a better isolation, I can build them in a separate substrate, completely different. You should look at, there are two bowls placed on the table. In each bowl, you have a different things. So, there is no connection between the two. But if you have a single bigger bowl, everything put in that, then they are sitting on the same surface. So, that is the difference between the isolated P well. So, what you do actually, this is analog, this is digital. So, there is something called deep N well, and what deep N well is nothing but you put a N well, wall of N well that goes deep down, and there is something called buried layer inside at the bottom. So, you vertical wall you create on both the sides, and then the bottom, and this is nothing but N type diffusion. So, your P is completely carved out of that. So, you create another P well inside the P substrate. So, this is called isolated P well. So, now this is N well, and you can think about, this is showing a top view, but at the bottom also you have the same thing. So, this will be completely separated out, this P well, and same thing is for digital. So, the two substrates are completely isolated, and there will be hardly any noise coupling between the two. So, before it reaches here, this will block, because this is N and this is P. So, there is no propagation which can happen between one P well to other P well, isolated P well. So, if you have this option, then always try to utilize this. and keep analog and digital in separate P well. So these are some latch up guidelines. Latch up basically happens, I mean, you can go and read the textbook. It's basically you have all n type p type diffusion, so it creates a PNP NPN junction, and that becomes a bipolar, actually parasitic bipolar. So back to back bipolar, it creates more like a latch kind of a circuit, and if one of the bipolar turns on, then it will create a short between VDD and ground, and that's a latch up. So the best way to basically, I mean, reduce the tendency of latch up is separate out the devices, and mostly this is created when you have both N channel and P channel placed together. If you have all P type and N type, then it won't happen. So those two bipolars are created between NMOS and PMOS, just like an inverter. Okay, in the inverter you have both NMOS and PMOS. So the tendency of latch up in inverter is high if both N and P are placed together. So the best way is that you try to isolate, create a difference between the two devices, don't keep them separate, or keep all the type devices closer, and then like all P types and all N types. So whatever in the ESDs, we most of the time we use NMOS and PMOS devices. Okay, so ESD is nothing but on the pad, so electrostatic discharge. So when the chips come back, if you connect your finger or any surface, actually it can discharge the charge to the pin. So and the gate cap is very small, so you can think the voltage created on that pin will be very high, like order of kilovolts. So that can puncture your gate, and that's why we use ESDs. And these ESDs, what they will do, they will basically take all the charge and dump to the ground before it reaches to the gate. So these ESDs are built on again these transistors. So when you are placing those ESDs, you make sure that all the N type and P type are side by side, not that, or never put like N and next like a P type ESD and MOS, because that may have a more tendency for latch up. Antenna effect. So what happens during fabrication? Plasma etching charges metal lines, and and these charge can basically dissipate to the gate, and they can alter your VT. So those charges will get trapped in the gate and they will alter your VT. So let's say it happens on one gate and it doesn't happen on the other gate in your diff pair, then the VT of the two devices will be different and it will create offset, and you can never get rid of this offset without using offset cancellation techniques and all those. So upfront we always try to reduce as much as possible. It's not that you don't care and okay, we have this offset cancellation built up, so that will take care of that. It's not like that. You always try to minimize it first, and then secondary precaution you take by having offset cancellation techniques and all this. And you know, dynamic cancellation is not applies everywhere. If you have a continuous comparator or continuous time op amp, then you may have a ripple problem in the output if you do dynamics. So that's why we always try to minimize the offset upfront before fabricating the chip. So these technology files, when you design your chip, when you lay out them, they will have some antenna rule which is called antenna ratio. So the area of metal over area of gate should be less than 70, let's say. This is for 0.13 micron process, which means if I put a large metal on this small gate, then tendency of this antenna effect is more compared to a small, because this large metal means area of metal is more, then it will have more charge. So I want to simply reduce that charge. So one way, like you can upfront try to make sure that this metal is area is not enough, but in case let's say you have routed it a long way, the area is long, area is large, then what you do, you put antenna diode. Okay, antenna diode is nothing but it's a diffusion, it's like a reverse bias diode. So you can, so let's say this is a positive signal, then you can connect N type of your diode here and P type to the ground, P side. So what will happen, this will never conduct, but any charge will get dissipated into this diffusion before it reaches to the gate. Okay, so whenever you have a diffusion, then it won't create a problem. The problem is created when you have a gate because it's insulated. There is no path for charge. But here you create alternate path for charge. So this is a one technique. Another technique we call it jumper or antenna killer. What you do, instead of routing in a single metal, you route in, so break the metal and put this patch of metal 2. So what will happen when the metal one is metallization is done on the first layer, what will happen? They are not connected. So the gate will see only this portion, it will not see the other portion. When you do the metal 2, then this is small, all the charges will be on metal 2 only, metal 1 will not have any charge that time. So that's how you create. So you reduce the area of metal basically by breaking them into different layers. That's it. So both are valid, you can use any of them. And when you are looking at a match transistor, putting them in common centroid and all those, this is very critical actually. You have to make sure that you take care of the antenna, otherwise it may cause a VT mismatch, and all the matching precautions you have taken in the layout, it will be of no use actually. Electromigration. So electromigration is nothing but it's basically when the high current is flowing into a metal, it will get heated up due to I square R losses and it will melt. So you have to make sure that the metal line, the width of the metal should be enough to carry that much current. So all the process technologies have rules for how much minimum metal or per micron meter width the minimum current or maximum current it can carry. And most of the time you have to look this, so they have a different spec at a room temperature and maximum temperature. So always look for a max temperature, and on top of that keep some margin. So that because electromigration, if it occurs, it will melt and your chip is dead. And when you have a 90-degree bend, then basically the effective resistance at the corner will be much higher compared to here. So what you try to put a patch here or have a 40-degree, 45-degree bend, just like you do in PCB. Okay. So this corner will get heated up more compared to this because you have a sudden bend here. So we try to get a smooth path by making it 45-degree bend. Then if you have a 3 modules connected, all have a current, so make sure when it's connected to the source, it has wide enough. So this one is carrying I3, but this line will be carrying I2 plus I3. So it should be wide enough to carry the total current. And when you are connecting to the VDD, this will carry all the 3 currents. So based on how much current is flowing, you have to make the width, or make the uniform based on the maximum width required. That will be the safest. Tiling. So tiling is mainly used for actually to avoid we talked about CMP. Okay, so when your polishing is happening, so and this base layer, oxide layer are soft actually. So if it doesn't see any metal, what would happen actually? It may damage that surface. So what we do, we distribute the metals if there is no. So there is a rule that in a minimum, let's say 50 micron by 50 micron, they will require minimum metal density. So, but what if you have a matched devices? You cannot randomly distribute the metal. We talked about how you put the demi metal match. So make sure that you put all the demi metals and make sure that density rule is met when you do your common centroid. Because what happens in the digital, what they do, they will run the script and randomly it will put metal patches here and there and they will pass the rule. But in the analog, you cannot do that. So when your chip goes on the top level for integration, where they have both analog and digital, then they will try to integrate your module with this. So what we do, there is something layer called anti-tile layer or tile block layer, where you match the density rule for meet the density rule for your block and put that tile layer, so that when they put the tile on the top level, they will not touch your module. Otherwise, it will screw up everything, all the matching and everything. So then on the capacitor, so if you have a D cap connected, and then you can stack up the metal, and these tilings, In any case, you have to put lot of metals to meet the density rule. So you can connect them in such a way that between two metal layers you can get additional cap and you will get it for free. So at the same time you can get additional cap and meet the density rule. High voltage layout design considerations. So if you have a high voltage and high current routing, so if you have two, this is a power FETs actually, don't put pad on the one side, either put them like on top of other and use double bonding, or put the pad in the center so that they will see only half the distance. So from current is flowing from this side to this side, it has to travel longer distance compared to this. Then again 45 degree bend you always try to use if its option is there. If it's not there, then try to increase the width at the corner and always put the place closer to your device. Don't route it long way because that will introduce IR. If you have multiple voltage devices, then always try to isolate them with the guard bars or guard rings. So, and this is your chip snapshot top level, and this is how it looks like. This is your die, then this is your package lead frame, and this lead frame actually, so when you bond your chip, so the pad will be something here and it will get bonded to the lead frame here, and the lead frame take the pin out. So these are your pads, these are bond wires and they will get connected here. So the package is usually much bigger compared to your die size, until unless you are using WLP package. WLP is wafer level package where your package size is same as your die size. So the pads will be sitting here on top of this like a flip chip, and package will be mounted on top of that. And this is how your different metal layers look like. First metal, second. So this is 3 metal. So the first, second and third. First, second and third, yeah. And then below metal 1 you have all the base layers, your diffusion layers, poly and all those. Okay. So if you know the PCB, it's easy to understand. It's similar, especially the metallization, multi-layer PCB. It's exactly same. The extra thing here comes here in the chip is the base layer, which is not in the PCB. Okay.